Okay, so we'll go on. Unfortunately for you, according to the criteria I described at the beginning, that I'm one of the speakers too. And I'm going to really follow up on Andre's talk, focusing on the microlensing aspect. So a lot of the introduction he already gave, so that will save me time. This is work that I will describe was led by my former student Yossi Schwarzwald, who's now at JPL, together with the OGLE and MOA and our local WISE teams, microlensing teams, and it was described in the paper that was published last year, led by Yossi and with me and Andre and the other members of the team. So if we try to look at the broader picture of why do we want to find planets via microlensing, it's for the same reason we want to find planets with the other techniques. It's to understand the general extrasolar planet landscape and to understand how planetary systems, including our own, formed. So this is a more or less updated picture of the known extrasolar planets with their masses and their separations from their host stars via the various techniques. And in the letters here, you see the planets in our own solar system. So Earth is here, Venus, Saturn, Jupiter, and so on. So one of the interesting things that you see from this plot is that most of the known extrasolar planets are still in a rather different part of parameter space from the planets in our own solar system, okay, with the exclusion maybe of Jupiter that's inside that cloud. Another thing you can see is that the red points, which are some of the microlensing planets that have been discovered, are probably the closest ones to the planets in our solar system. So that shows you one reason why it's important to find planets via microlensing. It's because we're probing a very important part of parameter space, a planetary parameter space, that's similar to the planets that we know and love and we're part of. Another way of looking at this same plot that was already done many years ago by Andy Gould is to renormalize the horizontal axis, dividing it by some mass, the mass of the lens star to some power, which is some way of indicating where the snowline is, the radius around the star around which ice condensates can form, and therefore there you can form giant planets. And when you do that, you can see that the microlensing planets all line up more or less around around one snowline radius, one or a few. Okay, so in our solar system, this corresponds to about 5 AU, but most microlensing host stars are M stars, simply because those are the most common stars in our galaxy. And so microlensing basically probes for planets in about a 1 AU region around low mass stars. So this is a very unique part of parameter space that's probed especially by microlensing. So it's another reason, it's very complementary to the other methods. Why does this appear again? Okay, so here's the first microlensing event discovered that Andre already showed, but up there you actually see the movie over about 2 months of the star flashing twice and then brightening again, and then going back to its normal brightness, very, very faint normal brightness. As Andre showed, these are the real data from this event in 2003, data from the OGLE survey in red and from MOA in New Zealand in blue. This will be my only slide, again, explaining how microlensing works in this animation, explaining this particular event. So the blue spot that you see running in the background, that's the position of the real position of the star. The 2 purple points are the lensed images, and one of the lensed images happens to pass next to a planet that's right there, which produces more splitting, more image splitting, more magnification. and produces these two so-called lensing anomalies from the regular Paczynski curve, the symmetric Paczynski curve. Okay, and you can also see plotted there that red diamond shape. That's the caustic structure that you see that every time the source crosses it, you get these formally infinite magnifications that cause these spikes. And this complex structure of the light curve is actually a good thing, because that means that you can reconstruct from an event like this, when it's well observed, the parameters of the system. The physically interesting parameters that you get from microlensing are the mass ratio of the star, of your lens star and your planet, and their separation. So it's actually quite similar to radial velocity planet measurements, okay, where you also get a mass ratio and a separation. With some degeneracies both there and here, but we'll maybe get to that later. Okay, so I'll very quickly show some additional of the historically discovered exoplanets through microlensing. I think all of them Andre showed as well. And this was the first planetary system discovered by microlensing in 2008. It's a Jupiter-like and a Saturn-like planet around, again, a lower mass star, an M star. And a few years ago, the second two-planet system was discovered. So again, you see now the light curve is even more complicated because of the more complex caustic structure. Okay, so today there's only about 50 microlensing planets that have been discovered, including the ones that I will mention today. And the question arises, why so few, especially compared to the thousands that have been found by other techniques? But of course, if we were asking this question only 10 years ago, 50 would already be a pretty good number. So we have to keep these things in perspective. Okay, but the reason why the number is so few is that until recently, the survey strategy for finding exoplanets through microlensing was the so-called first-generation survey strategy, which focused on finding events that promised to be very high magnification events, meaning they're going to be magnified to of order 100 or even more. And in fact, most of the events that I just flashed to you, for example, this one, or this one, or this one, if you look at the scale, let's go back. Okay, this is, there's like 4 or 5 magnitudes magnification. That's a factor of 100, 5 magnitudes. Okay, so these are all high magnification events. And the idea in this survey strategy was to find, to monitor a large area towards the bulge with these two observatories, with Ogle in Chile and Moa in New Zealand, with a low cadence that was possible, that was the only thing possible until recently, about once a night. Okay, so you look at the galactic center, you tile it as Andre showed, you find microlensing events, and a few hundreds were found every year, and then you focus on those that promise to be very bright, high magnification rays. You see the light curve starts to going up really sharply, and you predict that it's going to be high magnification. Okay, and in terms of this passage of the source star behind the lens star, high magnification means you're passing very, very close to the line of sight of the source star. Okay, so it would be this trajectory here. Okay, and in terms of caustic language, it means that your source is going to cut through the central caustic of the caustic structure that's produced by the combination of the star's gravitational potential and the planet that's somewhere out here, okay, that's producing this whole caustic structure that's kind of hard to see, okay? And the good thing, and the idea was then that once you identify such an event, then you alert a global network of small telescopes. As it turned out, many of them are even amateur telescopes that follow up this event to look for the anomalies the lensing anomalies that will indicate there's an extrasolar planet around the lens star. Okay? Now, why was this a good idea? So high magnification events are good because when you have this kind of passage, this very low impact parameter passage near your lens star, you're basically lensing your background star into an almost complete Einstein ring. Okay, and that means that if you have a planet anywhere along, remember that first animation I showed with the image passing near the planet and getting split? If your image is split into a whole Einstein ring, then it doesn't matter, anywhere you put the planet, it will perturb that ring and you'll see a lensing anomaly. So these events have very high sensitivity to planets projected anywhere near the Einstein. If there's a planet there and you have a high magnification event, you'll see it. Okay, so it's almost 100% sensitivity. And it's also good because making the source 100 times brighter than it really is can give you a very high signal-to-noise ratio, even when you're observing with very small telescopes. So that's good. And another reason that's a little more complex is that whenever you have these caustic crossings, you can also say something about the size of your Einstein ring and then translate your results into an actual mass for your lens star, not just a mass ratio. But that's another point. Okay, the problem with this approach is that almost by definition, high magnification events are rare. Okay, events that have a factor of 100 magnification occur about 1% of the time. Okay, so you're already throwing away the large majority of all your lensing events in terms of searching them for planets. Okay, and this translated to, if we're talking about, we said 650 events a year, microlensing events in total, so you're in advance already throwing away 99% of them. You're left just with 7 events a year that you monitor, and not all of them have planets in the Snowline region, so people were finding only 1 or 2 planets a year. Okay, and that was the reason why there were only, until a few years ago, there were only like a dozen or 2 planets known. Okay, and another problem with this approach is that this whole social construct of how you look for planets is very chaotic and subjective, okay? Because you have to decide in advance that something is going to be high magnification, and you have to alert your network. Sometimes you do it more successfully, sometimes less. The follow-up is very erratic. Sometimes the very fact that you get a lot of follow-up is related to the fact that people already noticed there's an anomaly, that there's a chance for a planet there. And then how do you account that when you want to turn all this into a statistical inference on the planet population, on planet frequency, and the planet mass distribution, and so on. Okay, so as opposed to these high magnification events that occur 1% of the time, the majority of microlensing events are low magnification events. Okay, such as this trajectory here for the source star behind the lens star, or this trajectory here. Okay, so they pass far away, they have low magnification. And the problem with these is that they have also low planetary efficiency detection. Okay, because this trajectory, for example, it cuts across the caustic structure, which you can barely see, that's here. So you would see an anomaly here. Okay, because the planet happens to lie here. But if for the same event the trajectory was here, you would see nothing. Okay, basically your image, none of your lensed images pass near a planet. So nothing happens to the light curve and you don't know the planet is there. So they have a lower planet detection efficiency compared to the high magnification events, but they are much, much more common. Okay, and in the balance, there's a potential for many more, an order of magnitude more, planetary detections using this method. Okay, so this led to the idea of second generation microlensing, which is to, instead of monitoring with low cadence the galactic bulge and spotting the events that are going to be high magnification, monitor the whole galactic bulge or a large region of the galactic bulge continuously, and get very, very good cadence observations of all the lensing events. Okay, and after the fact, you can then go to them and see which ones of them had anomalies and which ones did not. And as opposed to the previous very chaotic way of doing things, this would be a real controlled experiment for finding planets doing microlensing. Okay, so in 2011, we teamed up, meaning WISE Observatory here in Tel Aviv, we teamed up with OGLE and with MOA, and we found a region of the sky that would be monitored with high cadence by all three observatories. And at our respective longitudes, we can basically cover the galactic bulge during the summer 24 hours, basically. Okay, so we won't be missing any anomalies or not sampling those anomalies when they occur completely. Okay, and this is again the center of our galaxy. And these colored squares are the fields with the highest lensing rates found by OGLE in previous seasons. And on top of that, the red thing is the red area is the WISE footprint. So that's the area that was covered by all three observatories. And we did this for, here you see it here, the three different footprints to cover 8 square degrees in the galactic bulge. So we did this for actually 5 seasons, 5 summers, each time for about 3 months in a row. That's the time that we can see the galactic center from our rather northern latitude. So just to show you an example, here's an actual image from WISE, if we'll focus in, and here's an event brightening and fading again, and in the bottom row you see the difference image, so it's coming up and going back down. Here's the actual light curve from WISE, with about every night we have about half hour cadence, so we can see this of order 10 times a night. But you see the internight gaps over a period of about 2 months, or in this case it's even less, 1 month. And when you put the other observatories, you see you have this really nice and complete coverage of this event, except for the gap in the middle, which is full moon, where nobody observes. And of course, you can see the very clear planetary anomaly that's detected there. Okay, so we found many of these. Here are some typical low magnification events now. Look at the magnification on the left axis. So we're no longer talking about magnification 100 events. You know, these are just the typical magnification few events that one sees. And the data from all 3 observatories, and you see the nice coverage where in these cases there is no anomaly. Okay, these are things that were no planetary anomalies that were detected. Overall, our final sample after 4 seasons over these years was over 200 events. So they're all shown here over the 4 years. 29 of these are anomalous. We can see that it's not just a point lens, but there's something else next to the lens. In most of these cases, it's a binary star. There's another star next to the lens, a stellar companion, but none of them are likely planetary. So just some examples of these planetary discoveries from our Generation 2 project. So this is the one I already showed you. Here's another one. Several of these also Andre showed. So here's another one, sort of sub-Jupiter, Saturn or Jupiter planet around an M-dwarf. Here's a 4 Jupiter mass at around 1 AU. All these are around a few AUs. This is a slightly higher mass star, 0.8 solar masses. And most of these have been published individually. There's a super Jupiter. There's almost a brown dwarf. Maybe it even is a brown dwarf. 12 Jupiter masses, and so on. Okay, so as expected, we found a bunch of these. We found some interesting ones too, like this one that Andre also showed. This is again just a half Jupiter mass, 3 AU, around a 0.7 solar mass star. But as Andre showed, this was observed simultaneously by Spitzer from a different location in the solar system, so that it happened at a different time and at a different impact parameter. So you see this anomaly feature, this big dip. It occurred a few days earlier and at a different amplitude, and that is very useful for getting rid of some of the degeneracies in the physical parameters that always plague microlensing. And Andre already showed this one of a planet around one member of a binary system, and actually an Earth-like planet. Anyway, so we have this sample of lens stars and the detections of planetary anomalies around some of them. And the idea now is to carry out our objective of actually saying something about planetary demographics. What fraction of the stars that produce microlensing events host planets, of what masses, what separations, and so on. Okay, so the first step in a controlled experiment like this is actually to build an algorithm for objective anomaly detection. Okay, because without that, we won't be able to actually gauge what the efficiency of our experiment is. So Yossi did this, and this is an example of fitting one of these microlensing light curves with just a point lens microlensing curve. It's not symmetric because one of the things you have to take into account is the possibility of terrestrial parallax, the effect of what? 3 minutes? You're the chairman?
No, I am expert of the chairman's job.
But who appointed you? Oh, the chairman. Yeah, so I'm almost done. Okay, so this is due to basically to the Earth's acceleration around the sun. This has to be taken into account. Okay, but this is the event I already showed you, where the purple points show you how the algorithm actually detects automatically this very, very conspicuous anomaly that one can see by eye anyway. Okay, but we applied this algorithm to all the events, all the 200 and so events, and we found all the anomalous events. So here are a few more examples. You see all these very clear anomalies, and you see, maybe you don't see, the model fits to each light curve from which one can determine the parameters of the system. The interesting parameters, the mass ratio and the separation. Okay, so here are a few that are not so conspicuous, but these are still anomalous events where it's not a point lens. Okay, so the big question, of course, is what is the true frequency of planets around microlensing host stars that's implied by this detection of 9 planets around in 200 events in this generation 2 experiment. So to answer that question, as in any experiment in physics, you have to determine what is the efficiency of your experiment, and the only way to do that is through a simulation that takes into account all the observational parameters of your experiment. So we did that. For every event, for every one of these 200 events, we simulated a physical system where we add to that event planets of many different masses and of many different locations in the plane around the planet, ray traced through those, and produced these microlensing light curves, okay, which we then, quote, observed with the same parameters of our experiment, meaning with the same sampling sequences, including the moon gaps and everything, of that very event. We did it for each event with its parameters and with noise. And then we ran these events through our anomaly detection algorithm, okay, and found what fraction of those we found for every range in parameter space, or physical parameter space of the planets, we actually recover. Okay, so this is an example. For example, the central curve here would be the detection efficiency for one particular lensing event as a function of the mass ratio between the planet and the host star. Okay, so you see that, for example, for Jupiter mass planets that are around here, okay, you discover a planet if it's there 10 or 20% of the time. Okay, and of course every event has its own efficiency curve. And then if you want to ask what is the planet frequency for a given mass ratio, okay, you just take the number of planets that you detected with that mass ratio and divide it by the sum of all the efficiencies. It's very simple. And this is the main result of this experiment. Okay, this is the mass distribution of companions to the host stars, whether planets or stellar binary companions, as a function of mass ratio. So the dark area is the actual numbers detected. And you see that they're very low. Okay, these are everything to the left of this bin here. That's the planets. These are stars, right? So mass ratios of 1 or 1/10. These are stellar companions. These are the planets. And you have them written up there too. Okay, so there's brown dwarfs, Jupiters, Neptunes, and Earths. Okay, so these are the 9, and the numbers are very low. Okay, 1, 1, 3, 2, 2. And the unshaded histogram is what you get after you correct for that efficiency as a function of mass ratio that I just discussed. Okay, so of course, the lower the mass of your planet, the lower the efficiency, and therefore the higher the correction factor. Okay, so here at the very end, you have already quite very large correction factors of 100, which are of course very uncertain because then you have to know your efficiency very well. Okay, but here it's not so bad. Okay, it's just factors of few, and for the stellar binaries, it's small factors. You find everything when it's there. Okay, and the interesting thing that comes out of this is, first of all, because the numbers are so small, you can't really say much. I mean, you could pass a horizontal line through these points, right, and it would be okay, and that's just the result of the fact that we're still talking about very small numbers. Nevertheless, the distribution, the corrected distribution, is suggestive of these two populations that have already been seen in planetary studies and binary companion studies using other techniques, using RVs, for example. For example, in this famous study by Grather and Einweaver 10 years ago based on RVs, you also see these two populations that are separated by this so-called brown dwarf desert, okay, where there seem to be very few brown dwarfs in orbits up to 5 years, so it's more or less the same separations we're talking about here with microlensing, around FGK stars. Okay? And we're seeing a very similar picture, only the difference is that this is not a brown dwarf desert, if there's a desert here at all. That's arguable. It seems to be like a super Jupiter desert, rather. Okay, because remember, we're talking here mostly about M stars. Okay, so this mass ratio of -2 here corresponds to super Jupiters, while the white brown dwarfs actually do have a signal. Okay, as I showed you, many of the detections that we have of planets are of planets around brown dwarfs. Of companions to the lens stars are of brown dwarf companions. So there are really quite a few of these. So all this is suggestive of this the picture that we see in FGK stars simply shifting to the left for lower mass stars. Okay. Another thing you can get out of this is just the absolute frequencies which you can say now, thanks to the fact that we've done these efficiency calculations. So it looks like there's about 5% of these low mass stars host Jupiters, but now we're talking about the Snowline region, same as in our solar system, and about 10 times as many host Neptunes. Neptunes are the most common planets that we're finding in the Snowline region. So it could be, there's a large uncertainty there again. It could be, 25%, but it could be even 100% of these low mass stars host Neptunes. Brown dwarfs, as I said, are quite common, about 5%, much more common than we see in more massive stars. And the stellar companions are 10% or so. And again, all these numbers are quite consistent, except for the brown dwarf part, are quite consistent with what's been seen with other techniques. So it's filling in the picture, but it's doing it in a place of parameter space that wasn't quite well probed by the other methods. So here's my conclusions. This idea of second generation microlensing, which has been around for a while, it really does work. And you can do a controlled experiment for determining the planetary population using microlensing. There's about 5% of microlens stars that host Jupiters, about half of them host Neptunes. The super Jupiters seem to be playing the role of the brown dwarf desert. They're rare. While brown dwarf companions are actually more common than you find in FGK stars. And there's this hint, it's just a hint, not more than that, of this two population companion picture, a planetary companion population and a stellar companion population, presumably from two different formation avenues. Okay, thank you. Yeah.
Question. So usually people say 50% of stars are in balance.
That's true for solar mass stars.
So these masses you find that the relation is small.
And other people have too. That's been known for a long time. I mean, the fraction increases with mass, and when you go to more massive stars, it seems like they're all in binaries. I mean, ask Boaz about this. Okay.
Well, actually we know from Kepler statistics that the curve rises also beyond Neptune to the smaller masses planet. Can you say something about how this 50% divides between Neptune and sub-Neptune size planets?
Well, that's really where our statistics dwindle out. But shortly after our study, there came out another very similar analysis by the MOA group. They did things slightly different. Instead of doing a real second generation survey, they used only MOA data for detection. So they have incomplete coverage. They used a longer time period and fainter events. So overall, they have about 7 times more events that they've analyzed than we did. Okay, but they have only 2.5 times more planets, okay, because they're less efficient. So it's a slightly complementary way of doing things, and this is the analogous curve that they got. This was just published very recently. Okay, and one of their main claims is actually exactly pertinent to your question. They claim there's a break lowered of Neptunes. Okay, and here they give a lot of weight to these upper limits that they get here where they found nothing, okay, and then they put the correction on the nothing to get these upper limits up there, and they say, well, this is very significant. So I don't know if I believe this because it's all based, again, on 1 and 0 and so on. But there's possible that there really is a break there. At least that's the claim. Boaz. Sorry?
Just understand these numbers. Like 10% companion of one or a few percent one dwarf. What's the separation?
Yeah, this is in the range of separations. Well, in microlensing, you measure a separation scale to the Einstein radius. Okay, so
But in logarithmic, can you kind of say it's to one deck range?
yeah, it's between, no, it's less. It's from about 0.5 to 2. Okay, so and this corresponds in M stars to, 1 to a few AU.
And then this means this could be like, let's say 10% per deck, right?
Yeah.
Separation, so for a few decks, actually.
That's right. This is only the Snowline region, which is defined as, a few AU around 1 AU.
What's the fraction that are binaries or have bound walls? Could be actually much, few times higher than this.
If you look at all separations, of course, yeah.
Then, okay, so it could be again close to 50%.
2?
To 50% could be close. And the same, you're saying that low mass stars have much less companions. It's not clear from this at all.
Oh, okay, I understand what you're saying. Yeah, okay. The binarity of low mass stars, those measured by other techniques, is also in a limited range. Okay, so that's why the percentages are similar, I think. But I understand your point. I don't know the answer. What is the exact factor that you should need to correct by? Yeah, Viv.
What are you expecting to study from future missions like W first? And if you stress the technique, microlensing technique, to its limits,
Yeah.
what other observables are possible other than location and mass?
Well, I don't think any others are possible, but even those are not really possible yet. You get true masses and separations only for a fraction of those events where you've managed to measure so-called secondary effects, which are finite source effects, parallax, or some follow-up high-resolution imaging in which you can actually identify the lens star. Usually, you're degenerate in these parameters. Okay, but when you're not degenerate, then yeah, all you can get is the projected separation. Okay, this is not the orbit size. It's not the same thing, and the mass. Now, W first will be good because. Do you want to answer that question, Andre?
Well, I think that the number of objects with precise mass determination will be something around tens of percent. So 50%, something about 50% or something like that, because they will use different secondary effects. So they
Right. So
have some kind of parallax. In spite the W plus will be quite close to this will have some possibilities. Also, they will observe separation of star and the source after several years of mission, so they can have the size of Langstein ring.
Right. So the main advantage will be that you can see more of these secondary effects that remove degeneracies. Plus, you will be doing this in the infrared, where you can look closer to the galactic plane through the extinction, where both things get brighter and you have a higher density of stars, so you have more events. Yeah, so overall it'll be larger numbers and more precise determinations of the physical parameters. I think that's the answer.
Much more precise photometry.
Right, which will also help you for getting better parameters. Yeah. I think my time is way up. So the next speaker is Tzvi Maze. That's why. Thank you. That's